Okay, so I think we're live. So welcome to the Energy Symposium, February 1st, 2022. Our distinguished speaker today is Dr. Ben Krupowski from the National Renewable Energy Labs. He's the director of the Power Systems Engineering Center at NREL, who leads NREL strategic research in the design, planning, and operations of electric power systems. He has over 30 years of experience in the design, testing, and integration of renewable and distributed power systems, and has more than 150 publications in these areas with over 8,700 citations. He's also an IEEE fellow. Dr. Krupowski was recognized for his leadership in renewable and distributed energy systems integration and is the recipient of the IEEE Power and Energy Systems Ramakumar Family Renewable Energy Excellence Award. He's also an adjunct professor at the Colorado School of Mines and the University of Colorado and teaches courses on integrating renewable energy into power systems. So welcome today very much. And let me stop sharing mine and turn it over to you, and welcome, Ben, and thank you for your time.
Okay, thank you very much for having me here. Appreciate the invitation to talk today about renewable energy integration. Let me go ahead and share my screen. So today I'm going to be talking about integrating massive amounts of wind and solar into power grids. Before I get into the details of this, let's just take a look at where we are in terms of integrating renewable energy into the electric power system in the United States. So if you take a look at this graph from EIA, it shows you the primary energy source usage over the last 70 years. And you can see from 1950 to around 2010, we had this very steady increase in electrical energy use and a pretty straightforward amount of the various technologies from coal, natural gas, nuclear, and renewable energies. But some interesting things that have happened in the year 2020. 2020 was actually the first year where renewable energy supplied more than either coal or nuclear in the United States. And that's a pretty significant milestone at the end of the day. And since 2010, we've really seen a big change happening in the industry itself. We've seen significant declines in the use of coal as a primary energy source, and that's being replaced with natural gas and renewable energies. Nuclear and hydropower have remained pretty steady over that time. But let's dive a little bit more into this 20% renewable energy. If we take a look at that 20% renewables, you can see that a lot of the increase in that technology over the last 10 years is from increasing use of wind and solar. So in this particular graph, the wind is green, the solar is yellow, and you can see really massive amounts getting put into the grid. The amount of hydropower in the United States has remained pretty flat since the 1980s. And another significant thing happened in 2020. So this was the first year where wind power actually produced more electricity than hydropower in the United States. And we see this as a continuing trend where the increasing use of wind and solar will continue to go up. So what's really causing this increase in wind and solar? At the end of the day, the entire electric power industry revolves around the economics, providing low-cost electricity to consumers. And over the last 10 years, we've seen these really dramatic decreases in the total amount of costs from both wind and solar technologies. As you can see from the graph here, and even to the point where today in 2020 and 2021, 2022, utility scale wind and solar are the lowest forms or the lowest cost forms of new energy in terms of electricity per megawatt hour. Now what that means is that really large scale wind plants or solar plants, if you're going to go out and procure new electricity today, the cost from these wind and solar plants is the most cost competitive form of electricity. Now, of course, it does depend on what type of solar or wind resources you have at specific locations. And the other thing that you have to take into account is that wind and solar are not dispatchable forms of energy, meaning they are only running when it's windy or sunny outside. The other forms of energy, if you're going to procure a new plant, are a little bit more expensive, although they are dispatchable. So one of the things that we have to start looking at is how do we tie things like energy storage or battery technologies into these large-scale wind and solar plants to make them more dispatchable. The other thing that's happening across the United States is the real big push for more clean energy technologies to be deployed. And we can see that on a state-by-state level. If you take a look at the graph that you see here, the blue shaded states are states with clean energy mandates. And some of these states have very high clean energy mandates. For example, California has 100% clean energy mandate by 2050. The other thing that you can see in here is not only are individual states making these choices, but also utility service territories. So these green shaded areas are the utility service territories that have come up with 100% decarbonization goals. So even in states like North and South Carolina, you can see that some of the utilities there, like Duke Energy, crosses across state borders and has their own individual goals. So these are also driving these wind and solar deployments in the United States, besides the low cost factors. Also, the new administration has got these pretty aggressive national goals, 100% clean electricity by 2035 and 100% clean energy economy by 2050. I'm really going to focus on this nearer term goal around 100% clean electricity. So that's the electric power grid itself. And in the next 15 years, getting to 100% clean electricity, what does that really mean? So if we take a look at that and we think about it a little bit, we would include nuclear power in clean electricity, and we currently have around 20% of our energy provided by nuclear power. We have a 7% provided by hydropower, and then maybe we can replace some of our fossil fuel plants with other clean energy production. But at the end of the day, this potentially means that we're going to have an electric power grid that's probably got 50 to 70% by energy, wind and solar. And that's a significant change from where we are today, right? So if we looked at that number for percent wind and solar today, that was around 11%. And we were going to migrate this to a power system that's going to incorporate somewhere between 50 and 70% variable wind and solar on an annual energy basis. So what do we need to get to those levels? So one way to start this kind of process is to think about what do we already know about how to operate electric power systems with renewable energies. So, let's go and find out all the different examples and figure out what do we know today. So one thing that we know how to do on very small scale power systems is to operate with high levels of wind and solar technology. So this is an example here. There's a graph behind the pictures that show you system size. And this ranges from very small island power grids, as we were talking about now, where the electric power load is maybe 150 kilowatts, up to megawatt scale. As you notice here, this is in gigawatts along the bottom, so 1 gigawatt in the middle, all the way to 1,000 gigawatts. And 1,000 gigawatts is nominally the installed generating capacity of all power plants in the continental United States. The other thing to notice on here is the y-axis, which is telling us percent wind and solar energy. And you can see two other important features here. These red boxes, that is the instantaneous power at any particular time. So that means that throughout a day, a month, a year, at any particular period, say a 5-minute period, an hour-long period, the percent of wind and solar would be represented by this red box. The annual energy, now that's the entire, taking over the entire energy that's needed for an entire year, how much is provided by wind and solar. So we know that on very small island power systems, like here, an example, Tau Island and American Samoa, we can run that basically at 100% renewable technology. You can see they have a very large PV system and large-scale batteries that go along with this. Some of the larger island power systems like King Island in Australia and El Hierro in the Canary Islands, these also are getting to instantaneous levels up to 100% from wind and solar, and then between 65 and 80% on an annual energy basis. Now, some key aspects of these types of systems is that the renewable energy is paired with large amounts of energy storage. In the case here, these are batteries, and in the case of El Hierro on this island, they're using a pumped hydro system, so they're using stored water in this case. As we start to progress up the system size, you can see larger island power systems. So some of the Hawaiian islands like Hawaii and Maui, you can see they're operating at fairly high instantaneous levels and up to 40% on an annual energy basis. And then as we get up to much larger island power systems, the entire island of Ireland, which includes the country of Ireland and Northern Ireland, that's run as an entirely integrated grid, they're up over 30% on an annual basis. And for a while, we're limiting themselves to around 65% on an instantaneous level. Here in the most recently, we've seen some improvements in these instantaneous levels. Maui is almost up to 90%, and Ireland is now running up to 70% instantaneously. But the key here is we need to get these instantaneous levels up to near 100 in order to get the annual levels up above 50%. And so as we look at larger power grids, you'll see here a system like the Texas power grid or the ERCOT power system. This is data from 2019, where they were running about 26% on an annual basis and 58% instantaneously, and the Western Interconnect, that's a little bit lower because we have much less installed variable generation across the interconnect, but it's, as you can see, a much larger system. And then most recently here in 2020 or 2021, ERCOT was able to run their system instantaneous levels of up to 66%, mostly wind, but wind and solar on the grid. So as we look at the full spectrum of power systems, it's good to kind of understand, what do we know? We know how to run very small systems at very high levels of wind and solar, so we know it's possible. But we also know that the larger the system gets, the more considerations we have to take into account, and I'll discuss some of those that are needed in order to help us achieve these much higher levels of wind and solar integration. And so what we want to be able to do is come up with a variety of technical solutions that will eventually enable these power grids to run at 100% inverter-based grids from wind and solar instantaneously. And that would allow us to run at much higher levels of wind and solar on an annual energy basis. So it's not only the United States that's seeing these type of issues happening with wind and solar and understanding how the implications of running these types of grids. You can see an example of the Australian power grid here. So the Australian power grid is mostly along the eastern coast of Australia. And I'll focus in on this little portion of the Australian grid, which is in South Australia. But you can look here in October of 2020, they actually had a day where this red dotted line is the native load. And then this is the amount provided by various sources outlined here. This light yellow is actually distributed PV or rooftop solar photovoltaics. And this darker yellow coloring is utility scale solar. But you could see that there were several hours during this particular day where they could supply the entire amount of load from solar. Now they also kept a natural gas plant online. You can see that highlighted here in the gray. And this is then, this energy is exported to the neighboring regions here. They're keeping this on for system stability reasons that I'll discuss a little bit here further, but you can see that in the very near future, we will have days in Australia where they're seeing basically 100% of the native load supplied by solar energy. And we can start to see these types of situations happening in the United States. We see this often in Hawaii, this type of situation, and also in places where there are large amounts of deployed solar energy. So let's talk about the challenges of getting to these very high instantaneous levels of inverter-based resources and quickly discuss what do we mean by inverter-based resources. So if we think about how the power system operates, it's historically operated with these large-scale power plants. So whether it's hydro, nuclear, coal, natural gas, they're all using some form of energy and converting that to electricity through what's called a synchronous generator. So all these types of power plants have a synchronous generator inside of them. As we tie synchronous generators together through the electric power grid, that's similar to gears on a bicycle, if you will, in a mechanical analogy. But as we tie them together, they all run at the same synchronous speed and basically generate an AC power waveform at 60 hertz in the United States or 50 hertz elsewhere around the world. And if one of these generators were to fail, the rest of the generators interconnected would pick up that dramatic drop in generation and still maintain operational stability of the power grid. When we connect other devices like induction machines or inverter-based technology, they don't have the same synchronous functions that synchronous generators do, and so they have a looser sort of coupling back to the grid. So what we've been working on is the development of inverter-based technology. So inverters convert DC electricity to grid-compatible AC electricity. And if we put the right controls into those inverters, they can replicate some of the stability functionality that you would see from synchronous generators. And there is a big need right now really to think about how do we unify the operation of both synchronous generator technology and inverter-based technology like photovoltaics and wind turbines in such a way that they can be integrated at any levels and at any scales. So a lot of this has to do with the fact that if we start to reduce synchronous generators, say from a coal-fired power plant, and replace that with wind turbines and solar arrays, we want to make sure that we can maintain operational stability through the inertial constants in the power grid. So another example of kind of taking that idea around stability is this particular diagram here. So you can see the Western Interconnect of the United States. And what we're interested in doing is understanding if there's a problem on a grid this big, how does the rest of the generators respond to it and maintain the stable operations? So the two big parameters when we look at stability in the grid are voltage level, so those are represented by these colored dots, and frequency, which nominally is 60 hertz in the United States. So what happens, for example, if we lose a large transmission line? So in this particular case, you could see we'll take this line out of service. What that causes is an immediate voltage dip in parts of the Western interconnection and also a frequency dip. But if we embed the right controls in the deployed wind plants and solar plants, and they work together with the other synchronous generators online, they can actually arrest that decline in frequency and bring the system back into normal operations. So even though this is now out of service, the rest of the generation can reshare the load and maintain stable grid operations across the Western Interconnect. And we've done a number of studies that allow us to say with confidence that easily the Western Interconnect can survive a major outage with 30% annual energy being provided from these inverter-based sources. But if you think about from the beginning of the presentation, we need to move that to 50 to 70% of the annual energy. So how do we make sure that these systems will run and operate properly at those levels? So again, this is another quick graph that is something that we need to consider when we're looking at the controls that we build into the inverters in these wind and solar systems. We need to make sure that they are maintaining operational frequency stability and voltage stability across the grid. And so an example of that in here is if we add the right controls, we can let the decline in system-wide frequency not dip down so low and actually improve the overall grid. And we've done analysis to show that if you put the right controls in here, you can actually improve the system-wide response to frequency deviations. Some examples migrating from just modeling and simulation, but looking at how these systems can provide these types of grid services in the real world. I'll show an example here of a 300 megawatt PV plant in California. So NREL worked with the developer, which is First Solar, and the California system operator to show that these technologies can provide these fast response services. So an example here, that plant would normally be producing power along this green line. So as you can see here, it's running around 200 to 220 megawatts of output power. But what we were able to do is actually derate that system or take it off its peak power point by about 30 megawatts. So we opened up about 30 megawatts of headroom here, and then sent it a signal from the system operator to basically increase power or decrease power. By doing this, this actually adjusts the system frequency, and it helps maintain the operational reliability services being provided into the grid itself. So what we were able to demonstrate is that these PV inverters can actually be programmed to have very fast response characteristics and follow what we call automatic generator control signals from the system operator. And this is typically how large-scale power plants work. Now, I will point out here that we're obviously coming off peak power, so you are having a little bit of lost revenue when you do this. But at the end of the day, if you were to deploy this across the fleet of wind or solar systems, they all could just be doing very small amounts of these essential grid reliability services and regulation services. So we've demonstrated that you could do this on large-scale PV plants. We've also demonstrated that you can do this on large-scale wind turbines, having them very accurately follow active power control settings. So additional technical challenges that we see, in addition to the ideas around reduced levels of inertia in the grid and the inverter-based machines being able to provide this fast frequency response characteristics, is when we think about doing system protection. So when we think about protecting the grid from faults, we want to understand how to accurately understand that there's a fault happening on the grid, and then how to make sure that the system will actually be able to survive those types of conditions. Now, I'll explain power system protection here in about 2 minutes here, so hopefully you'll get the concept, but there's lots of details behind all of this. But if we think about a fault happening from a normal synchronous generator-based grid, when a fault happens, a lot of the fault current is delivered from synchronous generators. You can see here if the normal load condition was serving something like this, a fault happens here at time 0, you get this really big spike in output current from synchronous generators. When you do the same kind of fault for an inverter-based system, you actually get some different characteristics. And so in that case, you could get things where the inverter would recognize that fault is happening and disconnect very quickly, like you see in this red line, or it could ride through that fault condition for a number of cycles and then disconnect itself. But the point here is that either of these or neither of those look like the response characteristics of a synchronous generator. And so therefore, we need to come up with new ways of identifying that faults are happening on the grid when we have these high levels of inverter-based systems. And the coordination of all the protection devices needs to be understood and properly developed to handle these type of fault conditions with high levels of inverters on the system. Other technical challenges include the ability to black start the grid. So one of the things that happens now, right, if we take the grid offline, we need resources that are capable of forming their own grid, black starting from that blackout condition, and then going back in a sequence and doing a complete system restoration. So we know how to do that for large-scale grids with synchronous generators involved. There's a number of resources that are identified as the black start units that will help us bring the grid back online. But if we have lots of inverter-based resources, how do we do that similar type of a system? And we know it's possible. We've done it on small scales, but it's definitely a key component when we think about running grids with large amounts of inverter-based resources. So we've been able to demonstrate this at our own location here in Colorado, where we've operated 100% wind solar battery powered grid. You can see the megawatt scale wind turbines, about 0.5 megawatt of solar panels, and then megawatt scale batteries, and we were able to operate the building loads at this location. We actually operated it for 72 hours, completely on this 100% wind PV battery grid, and we were able to demonstrate black start capabilities from these devices. We devised some advanced control techniques to allow this that we think could be deployed across much larger scale systems. You can see a graph down here on the bottom of the solar coming up, this orange line, so that's producing sunlight. The gray line here is the load, and then the blue is the battery either being charged or discharged to maintain that load level. And then at nighttime, the wind is coming on and producing energy to provide energy to the loads. There's a variety of additional technical challenges. I won't go into too much detail here, but just to think that massive deployments of inverter-based systems that now have a variety of control algorithms operating in there, we need to think about how these control algorithms potentially could cause system-wide oscillations, and how we look to use these smart devices to actually damp out those oscillations across large-scale power grids. Now, one of the things that we're doing to tackle this particular problem is to think about how we bring together the inverter-based resources and the synchronous generator-based resources. And we actually have started a new consortium called the Universal Interoperability for Grid-Forming Inverters, or a UNIFI consortium. This is led by NREL, the University of Washington, and EPRI, really to address the fundamental challenges of seamlessly integrating all of these inverter-based resources with the synchronous generator-based resources. And this consortium really will focus on solving the R&D challenges, demonstrating these kind of concepts at scale, putting together best practices and standards, and training the next generation workforce for this future power system that will have lots of embedded inverters installed on it. So that kind of covered some very tight details on how we make sure these future power systems will operate with large amounts of inverter-based resources. But additionally, beyond that challenge, we have to think about the variability and uncertainty with wind and solar and how we balance the entire power grid with these types of resources. So I'll put up a little video here that's showing a day in the life of the Eastern and Western Interconnect in the United States. And in this particular future scenario, we've deployed lots of solar and wind. So the yellow dots in here represent solar. What you're seeing now is the sun setting, and that solar is actually being replaced by natural gas in this area. The blue here in the middle is wind. The light blue up here is hydro, and here the sun is coming up. You can see all the PV systems and solar systems coming online, and you can see energy flows throughout the Eastern and Western interconnects of the U.S. These little graphs on each side, these little wheels represent power flows going between the various balancing areas in there. The main point here is that you have to understand that the power system is not a static system. It's changing every moment in time. Loads are changing, generation is changing, and we have to make sure that we're able to meet the load and generation balance at every particular point in time throughout the entire United States to make sure that we're operating the system correctly. So there are a variety of ways to think about how to deal with additional variable resources being added into the grid, but we like to take sort of a systems level view of all of these options. It's really difficult to just come up with one very detailed solution that doesn't work from a system perspective. But what we want to do is create flexibility, to enable much more variable or variety on the generation side. So I'll go into much more detail in each of these particular areas if we think about the things we need to consider when we're adding in more variable generation. So I talked quite a bit earlier in this presentation about the ability of both wind and solar to provide a variety of grid essential reliability services, and these will be necessary to maintain operational stability across the entire grid. We also need to think about what's left in your existing fleet and how fast can they ramp up and down to match the variability that's happening with wind and solar. So hydropower plants, gas turbines, even coal plants can do some amount of ramping up and down. And you need to understand the implications of that ramping at a systems level. In addition to the generation side of the puzzle, we need to think about the load. Historically, we haven't done a lot of load control, but as we think about adding in more variability on the generation side, it makes sense to think more about how we do demand response, or responding to signaling that electricity may be cheaper or more expensive, and then using load more effectively to match those signals. And load can happen on the residential level, the commercial level, industrial level, and even the new load that's forming around transportation with deployments of electric vehicles. But one of the challenges that come from this is the fact that load is spread everywhere. So how do you actually think about controlling millions of generators, loads, storage? Compared to what we do now, which is maybe control tens of thousands of generators, how do we control millions of these devices? So we've done some experiments and thoughts and simulation around, well, what would large-scale deployment of distributed energy resources look like? And if you take an example of the Bay Area in California, maybe you might have 10 to 20 million controllable technologies in that space. And we've done large-scale modeling and simulation where we've actually deployed, in this case, close to 400,000 PV systems that you would see here. And just hang on one second. Step back. Okay, so close to 400,000 PV systems, as you see deployed on these little yellow dots across the Bay Area. On top of that, we have maybe 400,000 building loads. And on top of that, electric vehicles and charging stations, how these would all integrate together. And what we've been able to do is demonstrate that we can come up with control algorithms that would then control and optimize millions of deployed distributed resources on 1-second time steps. And this is critical when you think about how we're actually operating the grid itself. We want to be able to make sure that we're able to send signals out to these devices, have them react properly, and do that in a manner that keeps the grid operationally stable at all points in time. So in addition to the demand side of the equation, there's other things to think about. So something to really consider is how we actually do things like system operations. So that could include looking at how we do balancing across various areas and widening or expanding balancing areas, how we use sub-hourly scheduling and dispatch, how we bring in better renewable energy forecasting. In addition to that, the grid itself is a key thing to maintain operational stability. So how we actually are able to improve what is going on in the grid itself. So we have looked at several studies. I'll point one out here called the Interconnection Seam Study that looked at the seam between the Eastern Interconnect and the Western Interconnect. So what if we could actually build transmission lines that would move more power across this seam, if you will? So we looked at increasing the current back-to-back DC interties. We looked at putting in large-scale HVDC interties, or putting in some type of nationwide overlay. Each of these has got benefits and costs associated with it, but obviously to run many more things on electricity, we need to upgrade the entire infrastructure that is the electric power system. And then finally, one additional way to increase system-wide flexibility is energy storage. And so energy storage is being deployed rapidly now, especially large-scale battery projects. This is a picture of a 250 megawatt for 1 hour battery project located outside San Diego, California. And these are obviously going in lots of places around the country. And then things like pumped hydro, making best use of that. But of course, you need very specific geological formations to build out pumped hydro, but you can see that you can build them really large scale. So this is the Bath County pumped hydro system that's 3 gigawatts for 11 hours. With wind and solar having relatively low capacity factors, so something between 20 and 50%, that means that there will be this increasing need for energy storage to be used to deploy much more wind and solar. And we've started to look at how much more energy storage do we need. You can look at a variety of different energy storage options over here on the right. But if you think about what we currently have deployed, we have around 23 gigawatts of pumped hydro storage, maybe around 1 gigawatt of battery energy storage. But as you can see from some of these analyses, that to get much higher levels, above 50% on an annual energy basis, we're going to need hundreds of gigawatts of deployed energy storage in the United States. The other thing beyond energy storage to think about is seasonal energy storage. So we talked a little bit about some of those technologies like pumped hydro and battery systems, but if we need to move things around on a seasonal level, there's still a lot of development work needed in this case. So a quick example here, if you take a look at the Texas ERCOT system and we're to run that at 92% wind and solar, right? So 45% PV, 45% wind, 2% other renewables. You find if you do that type of analysis that you are overproducing a lot of energy here in the spring and fall time frame, and then you need a lot of power in the summer and winter. And so how do we store on a seasonal basis and shift this excess electricity over to when we need it? Those are remaining challenges when we get to this very, very high levels of renewable deployment. I'll also point out that there are various studies out there and available that have looked at how we start to transition the whole entire North American grid. So this is called the North American Renewable Integration Study, that looked at getting to 80% carbon reduction by 2050 and the different technologies that are needed and where they would need to deployed and the different options that we have available for doing these types of grids. Okay, to summarize what we've gone through here on this particular session today is really we are seeing this big shift toward getting to 100% clean energy goals. And each region around the United States is going to have a variety of resources to tap in to meet these goals. Now, obviously, one of the big levers we have is deploying more wind and solar technologies, and the fact that these are have really favorable economics right now are going to drive new installations and deployments across the country. I talked about these two main challenges with getting to very high levels of wind and solar. First, the inverter challenge, making sure that we can add more power electronic technologies while we're removing some of the synchronous generators, and that we can operate at close to 100% instantaneous levels of wind and solar. And then the larger challenge around balancing supply and demand and how we meet that across all the time periods throughout the entire year. At the end of the day, these are solvable challenges, but they are going to take working together to meet. And so I'd like to wrap up here with a quote from Stephen Hawking. "We are all time travelers journeying together into the future, but let us work together and make that future a place we want to visit. Be brave, be determined, overcome the odds, it can be done. And I want to leave today with that fact. This is a solvable challenge if we put our minds to it and get together and go quickly. So with that, I'd like to thank everybody, and I guess we will take some questions here. Thank you.
Well, thank you, Ben. Excellent, excellent. A few questions have come up from the audience. So one is concerning, I think, distributed or centralized control. So let me paraphrase. Would the interoperability of the inverters be based upon autonomy of each agent or each distributed resource, or how much centralized control would there need to be, or how would you do a hybrid system of some level of centralized versus decentralized? What about the control?
Sure. So right now, if you think about how we actually operate the power grid, it's fairly centrally controlled. We send out these automatic generator control signals out to large-scale generators, and they react to that. They do have some limited autonomy locally to do very fast corrections, but in general, we're doing centralized control. And the reason we can get away with doing that is the fact that we really don't control that many items on the power grid. And the Eastern Interconnect, maybe there are 10,000 big generators that we control. If we look to the future, that's got a lot more highly distributed systems. So distributed photovoltaics on people's roofs, distributed battery systems, and the controllability potentially of loads, you're talking millions and millions of devices. So that's where we investigated. We just don't think that centrally controlling and talking to every single device out there is really feasible. You don't have the communication infrastructure to do that, and you can do that in other ways. So one thing that we worked on, that autonomous energy grids that I showed you there, was more of a distributed hierarchical control where locally the technologies can talk and work together and come to some level of decision, and they're passing minimal information back up to larger grids. That solves a lot of problems. It solves the speed problem of how fast you can make decisions. It also solves the fact that you don't have to have a big communication infrastructure to make that all happen. And it also introduces some privacy into that. I don't need to know everything about what's going on at the lower levels as long as it's responding properly. So in general, that we think that the future really is going to evolve around some level of distributed hierarchical control to make this future energy system work.
Great,
Okay.
thank you. Next question was, how likely is it that geothermal resources will figure into the grid's renewable energy mix?
Well, there is some amount of geothermal out there, and it's being explored and tapped into. I think that the challenge is that it's not going to be at the scale that we are seeing wind and solar be deployed. So geothermal will be out there. If you have the very specific resource and can tap into it, it will be probably economical to do it at that location, but we just don't have it scattered across the entire country the same way that wind and solar is.
Okay, thank you. Another question is, and this may be related to the inverters for PV, or I wonder about AC transmission to DC transmission. What's the percentage loss on energy with DC to AC inversion? And when conceptualizing future build out of renewable capacity, how are you accounting for the capacity factor and loss of efficiency?
Yeah, for modern inverters today, their conversion from DC to AC is very high. It's 98%, 97, above 97% efficiency. 10, 20 years ago, it was much lower than that, around 85% efficiency. But modern power electronics on these inverter technologies are very highly efficient. So I don't foresee that being a big stumbling block at all in terms of that conversion. Now, when we look at other technologies like HVDC, where you're converting, say, from AC, then you're going to DC, transmitting that DC, and then back down to AC. Again, still the losses there are not as significant as they were in the past. We've had tremendous strides in power electronic development over the last 20 years. And so I don't see that as being a significant issue here at all.
Mm-hmm. Another interesting question came up. On over provisioning versus storage, I guess is the best way to paraphrase it. Are you modeling wind and PV systems at various levels of oversizing ratios, say nameplate versus interconnect size, as an alternative to using storage for balancing? Is there an optimal that you've seen? I know that it could be regional, it could be varying by season, but do you see some kind of rule of thumb appearing from your modeling effort on over provisioning?
Yeah, so this is mostly on solar, where you would oversize PV systems to give you flatter outputs over the day. At the end of the day, though, on solar photovoltaics, you know, that they are, no matter what you do, they can only provide power when there's sunlight, so they can't provide any power at night. So you're going to have to start to pair those with some type of energy storage if you want more consistent, or if you need, at a minimum, you're trying to shift a lot of that solar output a few hours into the late afternoon when the peak loads are happening. Wind, on the other hand, is, if you take a look at wind, it all depends on where you actually are, but it starts to look a lot more like a base load resource. When you put enough wind turbines out there, the variability, individual variability disappears, but you get much more production at night and other times compared to wind solar. So, you know, if you're generalizing things, wind and solar make a very good pair a lot of times, especially when you have big enough geographical areas that it averages out all the little variability from clouds and things of that nature. Now, I don't know of any good rules of thumb necessarily for how much to oversize those technologies so that you can eliminate energy storage. At the end of the day, we are going to need significant amounts of energy storage on the grid. The biggest challenge with that is energy storage costs money to put in. And so we need to think about ways of tapping into all those sources of flexibility that I discussed, including building out the grid, including tapping into variable loads to make the system work properly at these high levels of renewables.
You were talking about the cost of storage. Is there a breakthrough price per kilowatt hour for grid level storage that you see as something that would be a hugely monumental threshold? I mean, less expensive is always better for it, but is there some break point that you see that really would unleash it?
I think the break point is somewhere in the $100 to $150 a megawatt hour, which nobody really is at. I mean, some of the new lithium-ion batteries are getting toward that level, but again, most of the lithium-ion battery packs, for example, that one big 250 megawatt one I showed is only for 1 hour. So that's not necessarily designed to give you overnight energy storage the same way a pumped hydro system would be able to.
So breaking the $100 per kilowatt hour barrier?
$100 a megawatt hour.
Oh, that's, yeah. The best I've heard is a little bit less than $100 per kilowatt hour. Okay, and then again, everything's so we're way far off on that. Everything in power systems is regional, but are there any rules of thumb or interesting tidbits that you found from the modeling on an optimal amount of base load? You had in one of the slides, say 20% nuclear. Is that optimal or is that highly beneficial?
Well, you definitely, that's a good question. I don't know if there's an optimal amount of base load. Depending on how big of a footprint you're looking at in your resources, like I said, wind starts to look a lot like base-loaded systems. The nuclear fleet is what it is. You know, we've built it up and deployed it for other reasons, but I see us continuing to use nuclear power. It's a clean energy source. We still are going to use that. I don't know that building any much more than that 20% base load is helpful when you have the variability when you're adding in this variability of wind and solar. So even now, when we have nuclear power plants and the load goes low, we need to find places to push that electricity to, whether it's moving it around in the system or turning on additional loads or using it to pump hydro power in pumped hydro systems. So we need to, again, take a systems level approach to all the resources that we have inside the areas to come up with the right solutions.
Mm-hmm. Thank you. Another question, is technical availability of renewable resources being considered in the simulations? Or is this assuming infinite materials, minerals, et cetera?
So in this, at least in the simulations that I was showing there, we don't necessarily take that into account, but we have done other studies that demonstrate there are enough materials to build all of the solar that's needed and all of the wind turbines that are needed. Similarly on energy storage, but then you have to pick the technology that you're going forward with on energy storage. So there is a lot, I would say, of concern about trying to figure out how much energy storage do you need, and do you have enough of the materials handy. You know, the materials are out there, but that doesn't mean that they're quickly available. And as maybe people are familiar with, obviously the electric vehicle manufacturers that are putting together lots of batteries are looking for sources for all of those lithium-ion batteries that they're building out for the vehicle fleets.
Mm-hmm. And a question about combining floating solar with pumped hydro. Any kind of innovative modeling and results from combining those?
I haven't seen those two specifically paired together. We have done a lot of work on looking at floating solar systems. So floating solar systems are definitely being deployed to a large extent, not necessarily tied to pumped hydro systems, because if you think about a pumped hydro system, that water is moving a lot compared to just reservoirs where you would nominally put floating PV. I don't think you want too much up and down motion with all of those systems. So on a on a pumped hydro reservoir, especially the upper reservoir, that water level is changing dramatically. And so you don't usually put floating PV on those types of systems because you have so much change happening mechanically on those types of systems.
Mm-hmm. And then one example you had of a 200 or so megawatt system, and you derated 30 megawatts, so approximately 15%. Mm-hmm. That was all allocated toward a 4-second AGC, so it was reg up that it was reserved for. Is there any kind of mix, maybe instead of going all reg up, does there some response time faster than spinning reserve in 10 minutes that you'd see as being an optimal product versus all AGC controlled reg up? Yeah.
Well, so it's kind of a two-part problem. The inverters themselves we've demonstrated that the inverters on these big systems can move extremely fast, in fact, so fast that it's way faster than what I was showing you there on just an AGC signal. It can move even faster than some of the inertial responses on a synchronous generator. So these are very programmable electronic devices that can basically provide any of these services, whether it's fast frequency response, which I didn't necessarily show you in that graph, but they could be providing services that fast. They could be doing frequency regulation. Now, the reg response that you saw in the graph, you could program it to do up or down. Obviously, to do up, you need to pull it off its peak power point. It could be doing down regulation services without that piece. But it also all of this depends on what kind of market signals that you have available for these devices to respond to. And so, do you have the proper market signals out there that would encourage the vendors to make sure that these services are available? I don't know that there's a good answer for like what's the optimal level or how much should each of these be doing, because if all the inverter-based resources have this capability, then you wouldn't need them all to be doing that, 10% or 15%. They could just be doing 1%. And if they all did 1%, that would add up, and it would kind of disappear in the noise. But then also that may mess up how the market's working too. So there's a lot of little challenges that you have to sit down and figure out between what these devices can actually do in terms of the services and what markets are available for them to get reimbursed for providing the services.
Mm-hmm. Some more questions. Boy, we're getting a lot of questions here. This is great. Highly complimentary of the excellent presentation. So on nuclear base load, I guess to net this out, how rampable and load following are SMRs, small modular reactors?
Yeah, I don't think that I know the answer to that question. So I probably should pass on trying to answer that one. Although I would just say that in general, we have looked at how rampable are big nuclear plants, or can we take that flexibility into account and put byproduct on these nuclear plants. So instead of just producing electricity, they could be producing thermal heat and other products associated with that, or more closely tie, say, the production of hydrogen via electrolysis if the nuclear plant isn't needed for directly producing electricity for the grid. Now, how rampable are SMRs? I'm not an expert on that particular one. You can probably find that out online somewhere.
Well, thank you. Next one, high voltage DC transmission. How expensive, how much more, I guess you looked in the SEAMS study, how much more is your estimate of high voltage DC over the equivalent capacity high voltage AC?
So, it's interesting. I would say that, high voltage DC is the way you separate the two usually is how far are you transmitting electricity. So there's usually a break-even cutoff point somewhere around 350 to 400 miles. So if you're going longer than that, then HVDC is cheaper. Obviously, with an HVDC line, you have 2 converter stations, one on each side. You get some savings in the overall line technology itself, but you're paying for those converter stations. So historically, any line over 350, they would evaluate to see if HVDC makes sense. So you have to kind of look at where you're moving electricity to decide if you're going to be doing an HVDC overlay or you're going to be upgrading an HVAC system. There's a lot of, historically we have the system in the United States that has been built out a certain way. There's a lot of reasons why it's operated the way it does, including the reason why we have 3 independent interconnections. And you can look at other grids around the world, like the grid in China that for the most part has been completely rebuilt over the last 10 or 15 years with an HVDC overlay, and they've used extended use of HVAC technologies. They have pros and cons, and you kind of have to look at each situation, decide what makes the most sense for the various lines, whether you're going to pick HVDC or HVAC. Historically, HVAC will be much easier to do some types of control over because of the equipment that's around for those type of devices. when we look at HVDC lines, again, for the most part, these lines are all point-to-point. They're not multi-terminal, although there are a few that are starting to get built that are multi-terminal HVDC connections. So it really depends if you're just moving from one place to another or you want an interconnected network right now of which of those choices you would make.
Well, that's fantastic. So, and thank you so much for a highly informative talk. So many questions that we can't cover still. Thank you again. And so next week, we will have Stephen Otto, who's an economist at ISO New England, for an introduction to ISO New England, as well as a discussion on the capacity accreditation in that market. So join us for them. And again, thank you for our distinguished speaker for his excellent presentation. Goodbye.
Yep, thank you.